That's not the problem. The math is solved. The problem is this. We don't have the GPU to simulate the version.
No, bro, no. That's not the problem, bro. That is not, no, bro.
Why don't you build an accelerator for weather prediction? It will work. The physics is solved. We just don't have the computational power. Yeah.
How much computational?
Yes.
But how much computational power is in like that old woman in the village who looks at the clouds and says cloud of rain? Right?
Which is always inaccurate.
Yeah, the cutter's so slack, bro. That could be your 90, bro, or your 90. Come on, man. Sorry about that.
Okay. Sorry for the delay.
I did restart right now.
All right, so let's go back to where we finished off on Tuesday. Okay, so we sort of, I hopefully convinced you that, we talked about GEMMs and we talked about different layers and convolutional neural networks, for example, which we're going to focus on here. And then we basically said that the fully connected layers, so these are the layers where all the weights are connected to all of the activations. These typically occur in most networks at the end. These are essentially just matrix multiplications. It's a very straightforward mapping from this sort of, all to all, weight to all activations to sort of transforming that then into just a normal matrix multiplication. And if, batching affects the size of these matrices. So if only do one input activation or take one input image at a time, then you're only going to get a matrix by vector computation, which is inherently less efficient than having matrix by matrix. So we batch these things. And there's this n parameter. The more you scale n, the more columns we get in the input f maps. That gives us more inputs to operate on, and then more columns I get in the output f maps, basically giving me more results simultaneously. Okay, so this is a very common technique. This happens pervasively during training. It also happens during inference. The amount that we want to batch is tunable. Like batching huge amounts has blowback on inference latency. It also has blowback on training time because, algorithmically, if you're trying to, every time you sort of bump things together into this batch, right, you're sort of sending them all through the network and then back through the network at the same time. If you make that batch too big, the learning slows down because you're not actually seeing the updated result as you get to the next input image. So it has a negative effect on the training time, or at least the number of epochs you need to go. Training time, there's a trade-off because it runs more efficiently when your batch size is higher, but you generally don't want to do more epochs. And an epoch is sort of like a full pass through all of the input data that you're training your network on, okay? Okay, so we talked about these fully connected layers, and then we sort of pointed you out, okay, you can tile this. This is what you do in, this is what we did in class. You do this on CPUs, you do this on GPUs. We do this on GPUs with the shared memory. And there's a bunch of optimized libraries, right? Because this is a very common computation. So there's lots of different stuff. Lots of different backends that have optimized kernels where you essentially just pass it pointers to matrices, give it the size, and then it will run the matrix multiplication for you by essentially selecting its own sort of optimized kernel to do so. There's a paper on cuDNN that I'm going to post to Piazza after this class, and you guys should take a look at it before next class, because we're going to talk a little bit more about some of the GPU-specific optimizations that are inside some of these libraries. Okay, once we sort of get through the basics here. Okay. Questions on any of this before we move on? Today we're going to move on to the convolutional layer, and we're going to look at how this convolution operation, which is fundamentally different from a sort of straight up fully connected layer, which is just GEMM. We're going to map that convolution, the thing I'm asking you to do in your assignment, right? There's an algorithm, right, on how to do this. You can actually take that algorithm and turn it into a matrix multiplication. Okay, and I'll show how we do that in this next set of slides here. We alluded to tensor cores. This is sort of like marketing group from the white papers. the basic idea here is that instead of doing computations across individual scalar elements per thread, you can sort of do these group things across warps in the form of matrices, and there's specialized matrix engines that are built into hardware that modern GPUs take advantage of to perform essentially small subsections of the matrix multiplication very fast and very keeping as much data in register files as possible. These things have huge register files, and it allows you to compute a lot more data in a single cycle and be a lot more energy efficient. And so some of the high order numbers, this is on an older architecture now, probably this is like 8 years old. They've evolved quite a bit. They sort of started out saying you could only use floating point 16 data in these specialized units, because again, this is a specialized piece of hardware. They now are more flexible. You can use different dimensions for each of your matrices, and you could make your matrices bigger or smaller based on how wide your bit width is, because we've found that reducing precision in machine learning is an acceptable trade-off generally. And we'll talk more about this once we sort of read the Kudianen paper and then go into more of the optimizations in modern GEMM kernels. Okay. So another thing that has been proposed to accelerate GEMMs, so you'll find this theme, right, is that fully connected are definitely GEMMs. We're going to show you how to turn convolutions into GEMMs. So the whole game of accelerating machine learning today is accelerating GEMMs, accelerating matrix multiplication. There's this paper published by Google. Who's heard of the TPU before? Most folks, maybe like 3/4. Stands for Tensor Processing Unit. It's in, I think it's like 3rd or 4th iteration now. So basically, Google was paying NVIDIA way too much money to buy GPUs that were not super energy efficient when attempting to do inference, because there's a lot of extra overhead in GPUs that is not related to just doing GEMMs, okay? And they sort of hired up an entire division, an entire hardware division, because you're Google and you sort of have that reach through the stack and you have enough money to spin up essentially your own specialized hardware company. They hired away a bunch of people from industry, from academia, and then they built this thing called the TPU, which really isn't, it basically is a big systolic array. You probably have heard of systolic arrays from 565. The general idea here is that data is going to flow through the computational units instead of always going back to a register file, like in a normal ALU type or a typical ALU type system. Whenever you do a new instruction, you have to go read or write from the register file. That is your intermediate storage. In a systolic array, that's not true. You can take the output of one ALU and send it directly into the input of another, and you bypass the need to go back to some storage device, because it's sort of, you've got hardwired connections between ALUs. And then if you sort of orchestrate the way the data flows through correctly, you can, in a much more efficient way, without having to go back and forth through a register file, do the same amount of computation. As long as you know on every cycle, as I get to my next ALU, like the last ALU was producing something, it's going to go to the next ALU. I just have to make sure that I have the right data presented at that next ALU, and then I sort of fill the pipeline, and then I can very efficiently stream through data in this highly efficient way, as opposed to like having individual register files that are huge and suck energy and going back and forth. And so the core, the guts of the TPU is this matrix. They call it the matrix multiply unit. Okay, that's the yellow thing here. And what they're showing, and this is directly from the paper, and I will post this paper on Piazza as well. You should take a look at it. It's not a great academic paper. Academic papers tend to focus on ideas, right? And focus on like, key innovations. There's nothing super innovative about the TPU. Systolic arrays, data flow engines, these have been around for a long time, but they actually built it. And then, they looked at the challenges associated with it in, a real setting. Yes.
So last time I think we talked about like training versus inference.
Yeah.
So are there different architectures that are targeting like better at training versus inference, or is there just more work that's being done?
So in the early days, most of the accelerators were targeting inference only, okay, because latency was a huge problem. GPUs aren't great at latency. Okay, so in sort of quote unquote normal machine learning, the inference pass is a part of the training phase, because you have to feed the stuff through the network and then essentially back propagate the weight updates to update during it. That's why you train. But that phase of sort of sending the data forward through the network is the same as inference. So if you accelerate inference, you're also accelerating a portion of the training, but not all of it. So there are sort of specific accelerators that are designed just for inference. And for the TPU, the very first version of it anyway, it was pure inference. Okay. You could still do training, but you'd have to, it was just designed to go forward. So it would be not as efficient on training. So you'd still train it on the GPUs and then use the TPU for your inference. They've since revised CPU to try to make it more amenable to training. There are specifically, there's different trade-offs, different design decisions you make if you're thinking it's going to target training and inference versus just inference. Okay. Training, you don't really care about latency, right? So you can, similar to how CPUs make a lot of trade-offs to optimize latency, inference also has to worry about latency. Training, what matters is throughput and energy efficiency, not so much how long it takes to get one individual batch through the thing. So yes, the short answer is yes, there's different accelerators for both training and inference. By far, the most pervasively studied type of accelerator is for inference, because it is a subset of training, and it's also kind of a harder problem in some ways. And yeah. Okay. Other questions? Good question. Who's read this TPU paper? ISCA 2017. No other class makes you read this, right? It's written by this guy named Norm Jupe. What did Norm Jupe do? You all took 565, right? Somebody not here, yeah.
Didn't he work on some reorder buffers?
Yeah, he didn't invent a reorder buffer. He invented something that, when I say it, most of you should know what it is.
Oh, victim cache.
Victim cache. Who's heard of the victim cache? Yes, okay. Like basically, what is a victim cache? Putting you on the spot. Do you remember your 565? Yes, go ahead. No, Malcolm, go ahead.
It's like an extra kit. It's more a small extra cache to hold extra victims to them to get to reduce conflict misses.
Okay, so it's a smaller cache that helps reduce conflict misses. How does it help reduce conflict misses? Yeah.
Instead of throwing away the cache block on the first time you're supposed to replace it,
Yeah.
you put it aside in a structure that's closer to the L1 cache rather than closer to the memory,
Right.
so that you can replace it in case you access it again.
Sort of. Okay, so all right. Victim caches are trying to solve the problem of low associativity. Okay, everyone knows what associativity is, right? In a cache, the higher your associativity, the bigger your CAM is when you do your tag lookup, right? In one cycle, you need to know is this line in the cache, so you do CAM lookup. In the sort of L1, L0 levels of a cache, you don't want a wide associativity because that is costly from a time perspective and an energy perspective. You are banging on this thing at the rate of the processor in an ideal case. If you have all cache hits, you don't want a big, wide 64-way associative cache in that lowest level. You're not going to be able to keep up with clock rate. It's basically going to limit your clock rate. So you need a low associativity at the lower levels of memory. The downside, or the upper levels, if you're thinking of the pyramid like this, right, the L1 caches, the downside of this is that you get a lot more conflict misses because your associativity is low. So the idea behind a victim cache was you don't always need all the associativity across all of the potential ways. You only need it sometimes, and you can essentially just have, a normal L1 that has a low associativity, maybe even direct mapped. I think the original paper studied a direct mapped cache. And then when you replace from the direct map, instead of just forgetting it ever existed, which is what we do when we replace from a cache on a non-dirty line, we put that tag and the data into something called the victim cache, which has a much wider associativity, but its size is much, much smaller. Okay, so it's not going to be your L1 cache is like, 32K, then maybe you've got like let's say like a 20 entry victim cache that's fully associative or something. So it's not on the sort of critical hit path, but now you sort of smooth over a lot of the conflict misses associated with your direct map cache, because if you miss in direct map, you go check the small, widely associative structure. If you hit in there, then you can service the hit from there instead of having to miss. Okay, so very kind of clean, neat idea, has nothing to do with TPU, nothing to do with this class. But if you talk to people about like some of the great ideas in computer architecture, the victim cache is one of them. There's a band named Victim Cache, like some architects, I don't know, I think in Texas, like took the class and then like made a band and called it Victim Cache. Anyway, so Jupy is that guy. So he's been around a long time. Google hired him when they did this big hiring phase to try to do their hardware division, and he was the sort of lead author on this ISCA paper that has like, I don't know, 40 Google engineers on it or something, to all the people that helped build the TPU. Okay, so the guts of this thing is a systolic array, and then around it is a bunch of stuff to keep the systolic array busy. So, you know, if you want to sort of think about how this works, right, the activations are going to flow in through a bunch of buffers. You've got the weights sitting in some FIFO, so there's some orchestration logic in here to make sure that everything flows through at the right pacing. And so the weights will sort of conceptually flow in here, the activations will flow through here, and then, you know, the sort of data will get accumulated across the systolic array, and then, you know, have these little buffers at the end for the partial sums. And you can, you know, aggregate those as much as you need to do the particular matrix size that you care about. And then, of course, they have like specialized hardware to do the activations. So you do ReLUs, and I don't remember if they did anything other than ReLU inside this. And then they had some specialized hardware to do normalization and pooling. And then they had a bunch of local on-chip storage, because you don't always want to go back out to DRAM every time you're programming this thing. And it's implemented as a card, right? So it plugs into a PCIe slot, like they actually built this thing. You plug it into the same PCIe slot that you plug in your GPU. And, you know, they have an interface that plugs into the back end of, so Google uses TensorFlow, right? So if it plugged into the back end of TensorFlow, it probably also plugs into the back end of PyTorch now. That basically takes those codes, breaks them down into big GEMM operations, and then obviously there's some software to orchestrate the things so that way you can use it. Who's ever programmed a TPU before? So you can rent these. Like, at least you used to be able to. You can't buy them. Okay, Google didn't want to get into the selling of hardware games, so they sold it as a service, at least for a while. I don't know if they're still selling it as a service. When it first came out, there was like free academic licenses, and you could get some time on it to sort of play with it and see how it works. But I think today it's also still possible to get access to TPUs, but you can't go buy yourself one. At least last time I checked, it's sort of a Google exclusive piece of hardware. See some chats here. Oh, there we go. Look, your chat friends knew about victim caches. Who is this? Ishan. Anybody know this guy? Thank you, Ishan. You do? Okay, good. Good job. Okay. Sorry, Zoom folks. I'm not great about the Zoom. Checking the chats and whatnot. Questions on this? So I'm going to post this paper. I don't know that I'll give you any quiz questions on it, but I might, but I won't in class unless I tell you. So I'll post it, do take a look at it because it's interesting. And like I said, it's been revised a few times now. This is it's not 10 years old. It's what, like 2014, 7 years old now. Okay. What version of TPU were they on? Does anybody know? 6? You're just guessing. Nobody knows. All right. Okay. So people have built things to try to optimize GEMMs. That's the sort of high level point there. Now, a convolution is not a gem natively. Remember what we were doing with convolutions? We were taking this window that is the filter, and then we were sliding it across. So we're sort of redundantly reusing the weights. We have a much smaller weight matrix than we do for our activation matrix. And we're moving it step by step through the activations, performing this. You're not even performing a gem, right? You're actually performing like an element by element multiplication and then adding them all up, right? So it's not natively a matrix multiplication. It is a convolution, okay? But we want to use all of this matrix hardware and all of the matrix optimizations to run the convolution. So we're going to find a way to turn the convolution into a matrix multiplication, okay? All right, so let's go back to our 7-layer loop. This is what convolution does. Sort of iterating through all of those different alphabet soup dimensions that I showed you for what the filter width is, et cetera, channels are. And, this is not natively a gem. So let's take a look at pictorially what we're doing during the convolution. So you start out with your filter. So this is a simple 2x2 filter example. And then we've got our input fmap. And if we're moving sort of through this thing with a step size of 1, so you're going to place the filter, here in this diagram, in this region, then you're going to step over 1. So just move over 1 element, and then you're going to take this filter and multiply it by this section of the matrix, which is represented down here. And then you're going to do the same thing in the Y direction. So you step the filter down this way, and you multiply it with this section of the matrix, which maps to this quadrant. And then same thing for the very last quadrant. So if I'm stepping through with a window or a stride size of 1 here and a window size of 2 by 2, this is fundamentally the operations that I'm performing. Okay, so I'm taking my filter matrix 1, 2, 3, 4, then I'm multiplying 1, 2, 3, 4 by 1, 2, 4, 5, and then I end up with this one output element from my output matrix. Okay, so that's one operation. My output is going to be 2 by 2 as well in this example. Okay, given the way I'm striding through the data and given the size of the data. To figure out how big your output is, you have to go back to those equations, right? Because it's not obvious. It depends on how much you're striding. It depends on how big your filter is. It depends on how big your activations are. So the size in terms of n by n of your output fmap is dependent on these variables of how the convolution is moving through the data. Okay, so you're going to do a 2D dot product here essentially to turn this into this particular element. You do the same thing to create this element and so forth. And then you've sort of got the 4 elements of your 2-dimensional output. Does this make sense to everybody from a 2-dimensional convolution perspective? Taking this filter and moving it 1 cell at a time in both the X and the Y direction such that I cover the entire input matrix. Questions? Okay, so I can represent this as a 1D dot product if I just rearrange the way I think about the data. So I had 1, 2, 3, 4, and they're sitting here as this little square. If I just take that square and I turn it into 1, 2, 3, 4 as a vector, and then I take the corresponding vector that I would have created from this first quadrant cell, I'll get the vector 1, 2, 3, 1, 2, 4, 5, right? Because 1, 2, and 4, 5 are all in this same operation. And now I've turned this sort of 2-dimensional thing into a 1D dot product, right, between 2 vectors. Follow me so far? And then I do the same thing with the next one. Okay, so I do the same thing with 1, 2, 3, 4. So again, I'm redundantly reusing these weights, right? It's the same 1, 2, 3, 4 for each of these operations, but for the green anyway. Sorry for the colorblind people, I didn't actually create these slides. But then the content of the blue stuff changes. Okay, so the content of the blue stuff here is 2, 3, 5, 6, and that maps to the 2, 3, 5, 6 that we were doing over here. So I just took this thing that was 2 dimensions, which is a little bit hard to reason about how you construct matrix multiplications from this, and then I turned it into 1-dimensional dot products. And I did that by essentially choosing the correct elements of what we call the activation matrix. Each of these blue vectors that I'm creating is a different part of this input fmap. And what part is dependent on where the filter is during this operation. So now I've taken this thing that's 2-dimensional and I've turned it into essentially 4 dot products that are then going to result in a vector output, right? Because this is vector by vector. I will end up with this vector output of these 4 different dot products that represents the cube here. So all I'm doing here is taking something that was 2-dimensional and I'm turning it into a 1-dimensional operation. Follow me so far? Okay. This process is known as flattening or lowering the matrix. You may have heard of these terms. Okay, so you had this 2-dimensional thing, and then I turned it into this 1-dimensional thing, and so now I've got multiple operations that are basically redundantly reusing that filter and then doing it against different slices of my input fmap. Okay, so this is called a flattening. Now, if I flatten the entire thing, and then I represent each of these, right? So each of these were vectors, right? These are the vectors I pulled out to do the flattening. I take each of those vectors, and then I put them together. What does this start to look like? This is a matrix, right? This was the first vector I created from that first square. This is the second vector I created from that second square. And so now all I'm doing here is showing you how I took that 2D dot product, turned it into a 1D dot product, and then I shoved them all together to make a matrix, which will then result in this output vector. So now I have vector by matrix computation to do the to basically do the convolution. Okay. What's something you notice about this? Who's heard of a Toeplitz matrix before? Okay. Some folks. In the context of this precise operation or just outside of mathematics?
Math.
In math? Why did they teach you Toeplitz? You forgot why. Do you remember why?
I took a linear unemployed course.
Yeah.
And talk about different metrics.
Okay. Toeplitz is one of them. Okay. So this is called, a Toeplitz matrix, right? You're basically you're taking this matrix and then you're creating what's known as a Toeplitz matrix. Or you're taking these vectors and creating this Toeplitz matrix out of it. Now, what do you notice about this matrix? Is it pure gravy? Is this just like, is there something strange about the values in this matrix? Sorry? The diagonal.
The principal diagonal.
The principal diagonal, what about it?
It's symmetrical.
It's symmetric. There's lots of redundancy in these matrices. Okay. All of these numbers represent a different distinct number from our input activations. So if I do this sort of convolution and then I do this Toeplitzing of the matrix, I end up with, I'm highlighting the colors here. Again, sorry, colorblind people, but now we've changed the colors here to just represent all of the unique values, right? These 2s are actually the same bitwise value. The 5s are the same bitwise value. The 8s are the same bitwise value. So I've repeated data in this matrix to make it look the way that I want it to look. Okay, which is a potential downside of doing this, because before I was sort of, if you think about the operation of the convolution, you are using repeated data, because as your window moves, you're using one part of the original input fmap, and then if you only move by one, you're still using that same part you redundantly loaded before. So this redundancy is really just reflecting the redundancy in the computation of the convolution itself. But if you represent it as a matrix, then there will be redundant values inside of it. Okay. Questions so far? Yeah.
Can't you fix that by just using a step size that doesn't overlap in the original?
Yes, but changing the step size is algorithmically fraught, right? Yes, if you moved it such that the step would never overlap, then you would have unique data for every computation, but that's not usually how convolution works well. Usually you want the steps to not jump over you don't want the step size to be the same as the filter width, because the learning does depend on you having this sort of persistent amount of information as you move through. But you're right, if I jumped over all the data, then I would have unique values, but that will be dependent on my step size. Good observation. Generally, as system designers, we don't want to screw with what the machine learning people have done to make this thing learn correctly. So we don't want to say, oh, look, there's all this redundant data. Let's just increase your step size. Well, guess what? It doesn't work anymore. So you're doing a lot more. Maybe you've got sort of, one way you can look at this is that there's actually locality here too, right? I loaded this one value from the matrix, and if I can somehow capture that locality, I don't have to reload it from memory. Okay. You might naturally think of a structure on a GPU that does this, right? Like the shared memory. Okay. Other questions here? So now I've got a vector by matrix multiplication. Okay. To do this very simple convolution that I've showed you, where I've just got this one channel of filter, this one channel of input fmap, and I'm creating one channel of output fmap. But as you know, based on your decoder ring, we can scale all of these things. Okay, we can scale the number of channels, we can scale the number of output fmaps, we can scale the number of input fmaps through batching. So if we start out with this basic assumption that we're going to Toeplitz this activation matrix, so there's really no change to the filter matrix other than that it was 2D and now you're thinking of it as 1D. But the activation matrix does get this special reordering. And I want to add more than one channel. Okay, so if I am doing my straight up convolution and I've got two channels and I've kept all the dimensions the same, But now I have two channels of input and two channels of filters. These two channels have uniquely different values for the filters and uniquely different values for the F maps. They're essentially two completely independent computations. And so what I do to fit it into this Toeplitz argument is I append the channel to my filter, right? It's a completely independent operation. I can just put that independent work at the end of the first channel I had on the filter, and then I put that independent work at the end of the first channel I had in my Toeplitz matrix. So I basically then Toeplitz that second channel. So the top one is the Toeplitz of the first channel, and then the second one is the Toeplitz of the second channel. And now I've still got vector by matrix, but now it's bigger. Because now effectively my filter vector is much wider because I have more channels. Okay, questions so far? And then I still end up with the same output, right? When I scale the channels, it's essentially like merging all that information into the same amount of output data. So my output is still this 4x1 vector, 1x4 vector. Okay, questions? Yep.
Wait, so if you're doing two, if you're doing two separate convolutions, and yeah, the first one outputs, how do you separate those?
What do you mean?
So like we have
Like here?
oh yeah, yes, yeah. Oh wait, hold on.
So remember, you're going to take this filter, you're going to move it over this channel. You're going to take this filter and move it over this channel. Now, they're not completely independent because you aggregate those two results into this one cell. Okay, so that the computations to get the intermediate value or the partial products are independent, but then to create the output matrix, you have to sum them together. Okay, good question. Other questions? And that's what this will do, right? Now you've just turned your dot product wider, so now you're just doing more of it, and then the sum at the end captures that entire sum when you do the dot product of the row by the big column. Okay. All right. So everyone with me still so far? So if we add channels, we just make the filters bigger, and we make the sort of number of rows in the Toeplitz matrix bigger. But we can have multiple filters. So we're going to scale now F, the number of filters. And when we do that, we scale the number of output channels. Okay, so this is, what would happen. Conceptually what happens here in the convolution is that this filter gets, strided in the same way it was previously across this channel. But now there's also this other filter that we're going to apply to this same channel, but they're not going to be aggregated. Okay, they're going to be completely different discrete results, which is going to give us two output channels. So if I scale, again, this is going back to the decoder ring from Tuesday. As I scale the number of filters, I scale the number of output channels. Now, what do you think is going to change in our matrix analogy when I did this? What do I need more of now? An additional row in the filter matrix? Anything else? An additional row in the filter matrix now turns this from vector matrix into matrix matrix. Okay, so what's going to happen in my output? I'm going to get another row there too, right? So I add my other filter, and I do exactly as was just suggested. I add another row to that filter matrix that represents this other filter with its other values. I didn't do anything to the Toeplitz matrix, right? I scaled that when I scaled up channels, but as I scale the number of filters, I'm just adding more data that I'm going to slide across this thing. And I have to add another row to my output because now I've got a 2-row input, so I need a 2-row output. Okay, and this will give me now the two channels of my output. Okay, so now I've effectively turned matrix or vector matrix into matrix matrix. But we're not done, because natively there's not enough parallelism, right? You don't now that the size of the filter matrix is limited by the number of filters that you have, which is really dependent on which is dependent on filter size, and you don't have, we can scale this even further. Okay, so questions on this so far? So now we scaled filters, so we scaled channels, and we ended up making the rows bigger in the filter. We scaled filters, so we made the number of columns bigger. What are we going to scale next?
I had a question.
Yeah,
actually,
good.
About the terminology, I guess. So like in the output matrix, I thought, like each row is like that particular filter one aggregated over both channels, right? Or summed over both channels.
So the output matrix, forget two filters for now. The output matrix, if I only have one filter, is just a single row, right? And that is the aggregate of, that one filter across all of the channels. Correct.
So in the output matrix,
Yeah.
that first row is still like filter one convolved with all the channels.
Exactly. And the second row is filter two.
Okay, so I guess I'm just confused on like what exactly are we calling it the channel first? Like in the output, are both the channels sort of blended together?
So there's a difference between input channels and output channels. Okay. They're completely independent. Output channels is based only on the number of distinct filters you have. Input channels is based on whatever the last layer gave you. When we talk about this, it's always intuitive to think about the first layer and images having 3 different channels. But in reality, this data could be anything. It could be any n-dimensional data that has n channels associated with it. When you get into the guts of even just image neural nets, and you'll see this in AlexNet even, right? You'll go from like 3 channels, you'll blow up to 8. Like the channels tend to get bigger. They don't map to anything real anymore. They map to this internal state inside the neural net that's, conceptually picking out intermediate features. So I don't know if that answers your question, but there's sort of these games that you play when you design the neural net to scale the number of output channels that any individual layer will produce based on, based on conceptually what the next layer is going to need from this neural net. And it gives you more data, right? As I scale the output channels, I get more filters. So from a learning perspective, I have more numbers to play with. I have more dimensions with which to try to learn this unknown space, right? All of machine learning is trying to figure out like an approximation for some nonlinear function, right? Of like what the output should be based on the input. The more data you throw at it, the more knobs it has to tune. There's a trade-off here because like the more knobs you have to tune, the more useless knobs you have and the longer it takes to train. These are all the black magic of machine learning. Okay.
So for the next layer, then these two like these
Exactly.
channel, the input channel.
Exactly. So if I'm doing if this is my first layer, then I have 2 input channels, and then I also have 2 output channels. So then the second layer is going to have 2 input channels. Make sense? But that doesn't have to be so. If I just had 1 filter, then the next layer would only have 1 input channel. Make sense? Good question. Other questions? Okay. So here's the math. So if you go back to your decoder ring, and then you sort of think about all of the different letters that we talked about, right? As you scale filters, and scale channels, and scale the dimensions of the filters, and the dimension of the input map, you can precisely define if I have a particular convolution with a particular stride and a particular number of filters and input map, whatever, what is this going to map to in terms of a matrix multiplication? Okay. And that is very precisely defined. And these are the sort of equations that give you this. The last thing that I haven't actually talked about here in these sort of detailed slides is what? There's one more scaling factor that I've omitted here. FMAPS, which is what? What's this known as? Let's scale batching. Okay. So as I add batches to this thing, what do you think I'm going to do? I'm going to basically add columns to this, right? So this is one input FMAP. Envision this is one image coming into the network. If I had 2 images coming into the network, I would basically just double the size of my Toeplitz matrix. And then it would be completely independent data for this other image that I've batched together. So I can scale up the size of the number of columns in the channel sorry, the number of columns in the activation matrix by adding more batches, okay, by making the batch size bigger. Does this affect the output in any way? What do you think? More columns, right? As I scale here, I end up with more scaling over here. Okay, so as I add batches in, okay, I end up with unique data, new data that is my input matrix, and then that's going to result in more columns on my output. Okay, so pictorially, this is what happens as you scale n. So the n factor is here. So n is the number of inputs in your batch. In this example, we're just showing a batch size of 2. Okay, so this is one batch, this is another batch. And then as you scale the number of batches, you also end up scaling the width of the output matrix, the number of columns in the output matrix. Okay. And intuitively, you know, of course, this should happen because you're putting more images in there. So you should have more answers for each of those images that sort of get spit out by this thing. Okay. Questions on this? So you can take any arbitrary convolution and you can turn it into a matrix multiplication. And this is what almost all optimized convolution kernels on matrices of any reasonable size does. It turns it into a gem. Okay, and the process of turning it into a gem, there's different ways to do this. Obviously, this Toeplitz matrix is a pain in the butt. It's huge. You know, there are ways to create this efficiently and kind of on the fly, which we'll talk about when we read the Kudianen paper and then look into that a little bit more. Okay. Are there any questions on this? So this is a fundamental thing in systems-based machine learning. If you go to some job interview, they'll probably ask you about flattening in convolutions. Okay, that's what this is. You should know what that is, and you should know how it's done. Okay, I'm not saying memorize all of these dimensions, but if you did, it'd be good. You'd look real smart. But you know, this is such a common operation that any of you applying for any job that says machine learning XYZ, which is a lot of jobs out there right now, you should understand this lowering operation. That said, are there any other questions? Okay. Who has seen this before? A couple of folks. Okay. All right. So in addition to, okay, we're going to do GEMMs. There's many different ways to do GEMMs. We're going to fly over a few different algorithms that have been proposed, throughout, let's say, history, computing history at least, and some other ways to compute convolutions that are not just GEM based. Okay, so this is the game. This is where most of the computational time is spent in many of these networks. So obviously, you should go and try and think about how to make it faster. So the goal of doing different transformations. So the normal matrix multiplication, regardless of how much you tile it, is what complexity? N cubed, right? Standard N cubed algorithm. You've got this triply nested loop. You have to do these operations. This your matrices scale, everything goes to the cube. Okay, that's sort of the standard. Asymptotic, ignoring all memory kind of analysis that you're taught to do in like 608, right? 608 teaches you this, doesn't it? You guys are taking that class next. Okay, so, are there better ways to do this? Are there more nuanced ways to think about the computation? Yes, the naive way is not always the optimal way. So there's this guy named Gauss. So there's Gauss's multiplication algorithm. We've heard of this before. So this is applied if you've got imaginary numbers. So if we've got matrices that have real and imaginary components, if you do the matrix multiplication, you end up, you can rearrange it essentially to look like this. Right, because you have an A and a B and a C matrix that are real, and then a B and a D matrix that are imaginary. You can rearrange the computation. You can rearrange the mathematics such that you're trying to trade off multiplications for additions. Okay, if you know that multiplications are more expensive than additions, which anyone who took 362 should know, right? Because a multiplication is just a whole bunch of additions. So it will natively be much more expensive to do a multiply than an addition, no matter what you do, because you can give the multiplication as some number of additions. Then you want to reduce the number of multiplications in an operation and increase the number of additions. And so the way that sort of Gauss is able to rearrange the the matrix computation here, you end up doing in the baseline case, it's 4 multiplications, right? So 1, 2, 3, 4, and then 3 additions, 1, 2, 3. This is if you did it blindly. If you rearrange things in the way that Gauss proposed, I think this is like 1960s, then you end up with just 3 multiplications. So 1, 2, 3 multiplications, and then 1, 2, 3, 4, 5 additions. Okay. I'm not going to go through the derivation of this. If this stuff interests you, this is well documented in algorithmic textbooks. But the bottom line here is that this algorithm for real and for matrices that have an imaginary component can trade off the number of multiplications for the number of additions, which can be a win. Strassen, who's heard of Strassen? Okay, some folks do this in 608 somewhere. Somebody taught you this at one point?
I think in the math book.
In a math class, okay. So it's essentially a decomposition algorithm. So instead of trying to do the brute force matrix multiplication where you take the entire row and entire column and do the dot products on those, I can think of any arbitrary matrix of any size as being composed of submatrices. That's the sort of core idea. And so you can sort of think about A multiplied by B as being composed of these lowercase letters, which are 4 quadrants worth of submatrices. And then if I think about, so if I had a giant matrix A and then I sort of quartered it up like this, I will have 4 little matrices. And then the resulting C matrix, if I did the big A and B multiplication, will look like this, right? I can sort of think about, I could basically decompose matrix multiplication instead of on scalars to on matrices. That's the idea. So, if little a and little b and little e and little g are both matrices that are smaller, 1/4, of the size of A, then I can think about the upper left quadrant of C as being just the multiplication of those two, of these 2 little matrices added with, right? Because you're basically doing A, B by E, G, and then that upper left quadrant becomes just another smaller matrix multiplication. And you can apply this recursively all the way down to the smallest side. And if you do this, it's actually still n cubed doing it this way. But sorry, go ahead.
It's n to the 2.7k.
Yeah, yes. So it's slightly better algorithmically in the limits, okay, but it's still very close to n cubed. But there's a couple of other advantages of doing this. So if I think about, I can do some rearranging of the terms, okay? Again, a lot of math is like defining something precisely and then finding tricky ways to rearrange the terms to, trade off one thing for another. So in the baseline case here, where I've sort of done the simple Straussian and broken it down, I end up with 8 multiplies and 4 additions, right, of these submatrices. You can see how there's there's basically 2 multiplies for every quadrant and 1 addition. So you end up with 8 and 4. If I rearrange the AB multiplication to look like this, okay, so P5 plus P4 minus P2 plus P6, that's the upper left quadrant, and so on. I can define each of these different P's in this way, and if I do it this way, again, I've added a huge number of additions to this algorithm, but I've gotten rid of 1 multiplication, which is usually a win, right? Because multiplication is expensive. And what else is cool about this, what else is good about this, especially for machine learning, is that one of these matrices is usually constant. Okay, which matrix is usually constant if you're doing inference? What is constant? The matrix, the weight matrix. Okay, the filters are constant, which means that any operation inside this set of 7 equations that operates solely on the B matrix or the A matrix, depending on where you put your weights. Let's assume that they're in B, okay? Any operation that operates on one matrix only can be done once and then just reused. So you can sort of pre-process the weights to do this addition. So for example, this addition, right? E plus H. E and H both come from B, and if B is the weight matrix, I can do that once before I start running all my inferences, and I don't have to redo it every time. So I can even reduce the number of additions. So I can go from 18 additions in the worst case down to 13 additions because 5 of them are just on a constant matrix. And so this can be algorithmically better. And there was a paper that sort of showed this in relation to machine learning in 2014. Complexity-wise, this is better, right? So instead of being theta of n cubed, it's theta of n 2.807. Did you quote that number exactly?
I said 7, 8.
Okay, so you're wrong. 2.807. So it is, it is better. It costs more memory to do it this way. So there is no free lunch, right? You have to basically have all of these intermediate matrices, cost more memory. And there's some numerical stability problems as well, because you're not performing the same order of operations that you're performing in the sort of naive matrix multiplication. Okay. Another algorithm that can be applied is something called Winograd. And so this elides the whole matrix multiplication thing. It says, okay, fine, there's all these other ways to do matrix multiplications, but there's other algorithms that also achieve convolution. And Winograd is one such algorithm, okay? If you do this in a 1D space, it basically ends up looking like this. So you have your input, which we've sort of broken into these, this is a 2x3 input, and then we have a filter that is essentially 3x1. And then if you sort of do this math, you end up with this sort of 2x2 output. Okay, this is sort of the baseline 1D Winograd. You can do this. Right. So essentially, you're trying to represent the operation of convolutions mathematically, right? Instead of me showing you this thing sliding across, you can basically represent this with equations. And again, you can do some clever rewriting of the equations, right? So you could go from 4 multiplications, 2 additions, or 12 additions and 2 shifts. And then if you use the Winograd optimization, you can go to 4 multiplications and 8 additions if you know that you have constant weights. And again, there was a CVBR paper that said, look, you can do this, right? If I know the weights are constant, I can get rid of a bunch of shifts and additions and make it, more efficient. Now, we don't really want to do Winograd in 1D because we often have 2-dimensional data or n-dimensional data. So you can still apply Winograd in 2D. So this is if I've got a filter that is 2x3 or 3x3 in this case. And if you apply the sort of Winograd operation, you can reduce the number of multiplications at the cost, again, of having more additions. I'm not going to test you on the ins and outs of Winograd. Okay, there's sort of good algorithmic references for this. But for the purposes of this class, I want you to understand that, there is this other way to do convolutions that can optimize out terms similar to the way Strassen optimized things for matrix multiplication, okay? The nice thing here is that it sort of works on a small region at a time, and it reuses inputs, which is good for locality. And it's actually better sometimes. So this is data released from some marketing stuff from NVIDIA about, so this is BGG, which is an older neural net. And they took some of the layers, the dimensions from several of the convolution layers, and they compared the performance of a Winograd algorithm on a real GPU versus the performance of the best matrix multiplication of that same convolution. And sometimes Winograd is better, sometimes Winograd is not. So, they're showing here basically the speed up. So sometimes it's less than 1 on some of the convolution layers. It's greater than 1. I believe that this is on a GPU that did not have tensor cores. Tensor cores have sort of shifted it more so that the matrix multiplication is even more efficient. You can do some crazy optimizations inside the convolution kernels to also use the texture memory. Remember, we talked about this thing called texture memory, not usually used in CUDA, but you still can if you're a Ninja CUDA programmer and you want to maximize all of the on-chip SRAM, you have to go program texture memory. People don't tend to do that unless they're, working deep down in those optimization layers. If you did that, you can get, even more speed up by making use of the texture pipeline. Okay, so basically what is Winograd? Optimize computation for convolutions, significantly reduce the number of multiplies. And part of the problem here is that the fundamental computation changes depending on what the filter size and the output size is. Okay, the nice thing about turning everything to a gem is that it's regular. I know how big everything is going to be. It's going to be the same operation. I'm doing fundamentally different operations with Winograd depending on my filter size and my output size. So it can be a win sometimes. It's not clear from a performance trade-off when it is a win. What will happen in systems like cuDNN, they will have an optimized Winograd kernel that somebody at NVIDIA has wrote. They will have an optimized GEMM kernel that someone in NVIDIA has wrote. And then sometimes they will run tests, small tests, before they actually launch your PyTorch code to decide which of the two they should use for this particular kernel dimension. Sometimes they basically have done a mapping of this a priori. So they know if my matrix is, X by Y and my activations are, Z by W, then I know Winograd is going to be better, so I'm going to pick it. Sometimes I know this matrix multiplication is going to be better at the sizing, so I pick it. So that's part of what these libraries are doing. They know all the different ways you can perform these convolutions, and they know based on your dimensions and the machine you're running on, which one is likely to perform best, and they select. So you will find that if you looked at all the kernels that are launched, right? So I'm talking at the lowest, like NVIDIA level, just trace out all of the kernels in the profiler that are launched when you run some PyTorch code that implements a neural net, and then you change the neural net in some way, just change some dimensions, you'll potentially get a different set of kernels that are spawned. Or you change the architecture, right? Because maybe the Winograd is better on Volta, but then on Hopper, the matrix multiplication is better. So it will pick different algorithms based on what it thinks is going to get you the most best performance. And that is sort of all hidden from anybody doing the machine learning work. Okay, again, this is more Winograd stuff. I don't belabor this too much. Part of what we can highlight here is that you can do some pre-computation if you know that the weights are static. Okay, you can basically get rid of a bunch of the additional multiplications if the weights are fixed. Again, from the CVPR paper. Another thing we can do. You probably studied this in early mathematics about convolutions, right? We can do a transformation on them. We can do a Fourier transform. Because the math is simpler after you've done the Fourier transform than it is if you try and do the convolution in sort of normal space. How do you do Fourier transforms? Well, FFTs. Okay, so we take the data, we take the weights, we take the filters, we take the filters and we take the inputs, and then we do an FFT on them. There's well-optimized, known FFT algorithms you can run on GPUs. And then you basically get the output, and then it becomes, instead of being this like really crazy convolution where I've got to like slide this window over everything in the real space, if I go to the transformed space, it's just a simple multiplication, right? So it vastly reduces the number of operations once you've done the transform. The downside is I have to transform both the inputs, and then I have to transform the output. So I have this sort of lag to get into the Fourier transform space, and then this lag to get back out. Sometimes this is worth it. So we've got matrix multiplication, we've got Winograd, we've also got Fourier transform. Sometimes you're better off doing this Fourier transform than doing the matrix multiplications. So the downside is, right, you convert the filter into the filter and the input into frequency domain, and you have to convert it back at the end. If you think about the algorithmic complexity here, to do the direct convolution, it's n squared of this is the outputs, I believe, and then this is the filters, n squared of the filters. And then if you do this FFT computation, then it changes it such that it is independent of the filters. Okay, so if you do it in FFT, the filter size doesn't matter as much. So that means that the computational benefit of doing the FFT will decrease with the size of the filter, okay? Because if the filter is huge, right, then the baseline computation starts to become super expensive because the filter is a factor when you're doing the sort of normal convolution. If the filter is small relatively, right, to the outputs or to the input activations even, then you're better off because it's sort of so FFT decreases with decreasing filter size, right? So as the filter gets smaller, the benefit of doing this gets less because forgetting the filter size doesn't matter as much. In practice, the filters tend to be much smaller than the inputs. Okay, so then this isn't chosen frequently, but it is possibly chosen in some instances. And there were some papers on this. Okay, yeah, so this is the problem with FFTs. I don't want to belabor this too much. So QDNN, which is the paper that I'm going to get you guys to look at for next lecture, and I will give you a quiz on this, all right? It's a paper from 2014. It talks about a bunch of these different transforms and the trade-offs and trying to do convolutions with them. this is the sort of optimized backend. So this is what PyTorch uses, okay? Doing machine learning on GPUs today is like a tower of abstraction. People who write people at Facebook, people at, whatever company is trying to use neural nets, they don't know anything about CUDA in general. They don't have to. They just need to know how to program in PyTorch or ask ChatGPT to program in PyTorch. And then in the back end, like there's a bunch of system software that links together all that PyTorch with optimized libraries from vendors, one of which is cuDNN. And this is the sort of software layer that's doing all this picking of like, these are your matrix sizes. I know what your network looks like. I know what the inputs and outputs are going to be. I'm going to go pick from the plethora of kernels that I know are optimized for these different sizes. All of this sort of happens in this library. So this is where all the systems work is done to try to make that code run as efficiently as possible. And the gains here have sort of been ridiculous, right? So this is like this is a while ago now, but as machine learning was taking off, this is sort of that time frame when things started to become a lot more popular and cuDNN was released. You've got like a 60x faster training in 3 years. That pace has largely kept up, especially if you play games with the data width, which we have been. You basically keep getting better and better training because the software and the hardware are both working together to get you faster and faster training throughput. So once we start doing linear algebra, there's a bunch of mechanisms, there's a bunch of frameworks you can use to try to optimize things statically and dynamically. There's a DSL called Halide. This was released by MIT. So these slides are from MIT. So there's a high bias towards MIT-based tools. So there's Halide, which is basically this linear algebra DSL. TVM, which is tensor vector machine, which again is another sort of domain-specific like language. Time loop, which is something that I think Emmer had produced as well. So there's lots of different optimization tools you can apply to try to make this linear algebra go fast, especially if you're chaining things together, et cetera. And that's it. All right, for this slide deck. Questions? Yeah.
We heard of last year's paper by Google Alpha Tensor, where they used reinforcement learning to optimize Strasson's algorithm, and they were able to reduce complexity from n to the 2.8 to n to the 2.7.
Really? I have not read that.
They were like able to transform one of the multiplications into addition.
Really? And no one had found that in the
in like 50 years.
70 years of that thing being around? Okay. Yeah, we're doomed. Other questions? I'm early. I'm not going to start anything else today. So if you have any other questions, I'll answer them. Otherwise, class dismissed. You guys can go do something. But do read that cuDNN paper. If you Google cuDNN, you can find it. I will send it on Piazza. Read it, and I'll ask you some questions on it at the beginning of Tuesday. And I promise I will actually have a quiz on this. So please do take a look at it. Okay? That's it. Have a nice weekend, and we'll see you next week. All of you, the flattening question on any job interview that you have from now on.